Yes. Okay, then. Okay. So I welcome you all to this session on Fourier analysis. That's module number 3, what we are going to discuss in today's class. And we will be starting with some few numerical problems. And we had a bit of gap. Okay. So I want you to revise the concepts which I have taught you for the Fourier analysis. And it would be better that you can brush up a bit, okay, as we proceed on. And I'll be teaching you how to solve certain Fourier series problem. Okay, so we were starting with the continuous time Fourier series. Okay, and later on we had some corollary also being discussed. The first corollary which was discussed was the orthogonality. Okay, so next one was the real function. Okay, so along with the magnitude and along with the angle, and the real periodic function which was to be discussed there, and we had the complex Fourier coefficient also being discussed. Okay, so we had one simple problem that was being solved, and we had discussed the three corollary concepts there. Okay, so let me proceed in today's class as we already did with some of the properties also, and I want you to brush up a bit. We had completed with till time differentiation. Okay, so let me move on to the time domain convolution and also the modular theorem. Okay, so we generally say that to be modulation theorem or the multiplication theorem, and later on one of the important concept, that is Parseval's theorem there. Okay, so that is with respect to the power spectrum or the average power, what you are going to determine from the given signal. So that is how we are going to confirm using the Parseval's theorem there. Okay, so let us begin with the functions, that is the properties of the system there. Okay, let me start sharing my screen now. Okay. Okay. Yes. Let me share it. Yes. Okay. So what are the concepts that we are going to discuss in today's class? First one, it is the time domain convolution. Okay. So that is with respect to the properties. Okay. Again, I repeat, again, we are talking with respect to properties here. So it is the time domain convolution. That is one thing that I'm going to discuss in today's class. And later on, we are going to proceed with multiplication theorem. And at the end, we are going to start with the... Yes, I think someone has joined. Okay, so time domain convolution, modulation or multiplication theorem. Okay, and later on we are going to do with the Parseval's theorem. Okay, so now once I talk about the time domain convolution, one thing you will be having is I have the continuous time signal, say x of t, and its Fourier series is x of k. Okay, after you take the Fourier series, you will be having x of k there. So similarly for y of t, you will be having y of k. Okay, so you will be having y of k. So x of t is there, one, and the second one, which is y of t. X of t, you have the continuous time signal that is there, and similarly you have one more signal, that is y of t. After taking the Fourier series of it, you will be getting y of k. Okay, so now what is the new signal there? That is z of t. Okay, so how you will be getting it? It will be the convolution operator. Okay, so the convolution operator, what is the main difference here? We are going to perform the circular convolution. Okay, so I'll tell you what is the circular convolution in one of my videos. So the part of circular convolution is nothing but one of the signal, one of the continuous time signal which is there, you will be able to change the signal by keeping one of the signal as the constant. That is a discrete time sequence. You are going to take it. I'm talking about discrete time sequence. So you are going to change the one of the signals variation there. Okay, so you are going to keep, for example, you will be having x of t as some u of t. Okay, and y of t as some u of t plus 2. Okay, so now if you want to take the convolution, so you are going to change it as u of t minus tau. So that is x of t minus tau if you want to take it. So that would be u of t minus tau. So changing t to t minus tau there. Okay. So now this is the circular convolution that you will be using it there. Okay. So again, you will be having z of t, which is the convoluted part of x of t and y of t. So where it represents the circular convolution, where it represents the circular convolution. Okay. So now by omega naught, right? So 2 pi divided by omega naught. So z of t is this one. Okay. So now if you take the Fourier series of it, so that is z of t, by taking the Fourier series, what you are going to get? You are going to get t into x of k into y of k. Okay. So t into x of k into y of k. So that is z of t. So you have a z of t that would be equal to x of t convoluted with y of t, that would be equal to t into x of k into y of k. All right. So this is what we are going to prove it now. That is nothing but the time domain convolution. So this is the proof there. So this is what you are going to get once you have the circular convolution operation being performed on z of t, where you will be having two signals, that is x of t and y of t. Okay. So now let me proceed with the proof here. Okay, so let me proceed with the proof. So what do I need to do now? I need to perform the integral operation. So why do I need to perform the integral operation? It is the continuous time signal that I'm taking. Okay, so I'm taking the continuous time signal. Okay, so that's the reason why I need to perform the I need to perform the integral operation. Okay, so let us proceed with the proof. Okay, so now you will be having the some assumptions that you need to make, assumptions where you will be having x of t and y of t having the same fundamental period, that is t equals 2 pi divided by omega naught. Okay, so it is said to be assumed to have x of t and y of t, and also its circular convolution, that is z of t, having the same time period. Okay, so the time period of all these three signals have said to be having the same fundamental time period, that is fundamental time period t, that would be equal to 2 pi divided by omega naught. Okay, so now how do I write z of k? What's the definition of z of k? Okay, so how do I define it? That is 1 divided by t integral, okay, over the time period. Fine, that is z of t multiplied with e power minus j into k into omega naught into t dt. Okay, so z of k, that would be equal to 1 divided by t integral under the time period. Okay, that is z of t into e power minus j into k into omega naught t dt. Okay, so now how I can replace that z of t here? So this z of t, how I can replace it is, that is 1 divided by t integral over the time period. Okay, so that is x of t having the circular convolution of y of t. So I'm going to replace it with z of t being written as the circular convolution, right? So that is what we had defined. Z of t would be equal to x of t convoluted with y of t. All right. So now e power minus j into k omega naught t dt. Okay, so that is there here. So moving on to the next one. So what is the definition of the convolution there? General convolution or circular convolution here. What I'm talking here is x of t convoluted with y of t. So that would be equal to integral. I'm talking about the time period here. So now when I talk about the time period, okay, so earlier it was with respect to the axis, that is the time axis here. So I'm taking a new variable here, say L. So that is y of t minus L dl. So here you are talking about x of L. Okay, so here L, what we represent here is, this is the new sequence, that is L, which is there. So I am talking about the new variable, that is x of L into y of t minus L dl. Okay, so now I'm going to substitute this equation back again there in the z of k equation. What I'm going to write now, that would be equal to 1 divided by t integral. So here I am talking about t as the time period here. All right. So now here it was the convolution part what was to be written, and it is e power minus j into k omega naught into t dt. So here what I'm going to refer is this equation. Okay, so let me write it here with L equals t x of L, okay, y of t minus L dl. Okay, so that is what I'm going to write, and under the brackets I'm going to have that circular convolution being replaced, and you are going to have e power minus j into k into omega naught t dt. Okay, so that is what you are going to have here. All right, so now let me change the order of integrations. Okay, so how do I change the order of integrations? That is z of k, that would be equal to 1 divided by t integral L equals t. Okay, I'm going to take one of the signals, that is x of L. Okay, and again integral, that is t equals, under the time period, that you are going to have it as y of t minus L. Okay, and e power minus j into k into omega naught t dt. Okay, so this is one of the integral that is there, and you are going to have dl as the outer differentiating property with respect to this whole integral. Okay, so this whole integral will have dl. Okay, so here you are going to have the variable. Okay, you just match it here. Here you are having small t and it needs to be integrated with respect to dt then. Okay, so here you are having L, and what you need to do here is you need to integrate it with respect to dl then. Okay, so again let me replace it here. I think I have missed that one more thing. I'm sorry. Okay, this is t minus L. Okay, so now let t minus L to be replaced there. So simple thing what we are going to do here is, so t minus L can be replaced with one more variable called as m. Okay, so what you are going to do, you are going to have dt. Okay, so differentiating with respect to time, you will be having dt that would be equal to dl there. Okay, so that is what you are going to do here. All right, so dt would be equal to dm. So that is z of k, that would be equal to 1 divided by t. Okay, so that is integral L equals t, that is the time period of new variable, say L. Okay, so that is x of L integral the new variable, that is m, that needs to be changed, that would be under the time period. Okay, so now what needs to be written? Okay, so you're going to have y of m. All right, so y of m e power minus j into k omega naught. Okay, so this is m plus L. Okay, so this is m plus L. T would be equal to m plus L. All right, so this is what you are going to get it there. And dm. Okay, so this integral you're going to have it dm, and this one is dl. Okay, so now let us expand this exponential function over here. That would be 1 divided by t. Okay, so that is integral L equals t x of L. Okay, so what do I need to do? E power minus j, carefully I'm writing here just to make you understand, e power minus j k into omega naught into L. Okay, k into omega naught into L dl. Okay, and next I'm going to have m equals t, that is the time period that is there, and I'm going to have the other signal, that is y of m e power minus j into k omega naught into m dm. Okay, so that is there. So look at the definition of x of k that is there. So you are going to have 1 divided by t. Okay, so 1 divided by t. Okay, so what you are going to have? You are going to have this function. Okay, so you are going to have this function, that is t into x of k. So why did I write t into x of k? X of k was written as 1 divided by t integral over the time period x of t. Okay, so that is the thing. The x of k was written as 1 divided by t integral time period x of t e power minus j into k omega naught t dt. So similarly, t is being multiplied there on the left hand side of the equation. So you are going to get 1 divided by t. Okay, so this is written as t into x of k multiplied with again t into y of k. Okay, so one of the t gets cancelled. and you are going to be left out with t into x of k into y of k. Okay, so this is the circular convolutions proof and the time domain convolution what you are going to apply here. Okay, so let me explain it one more time to you just to make you understand. So we are having a proof that needs to be done for time domain convolution. Okay, let me write here. Yes, so this is the time domain convolution. The first proof what is there is the assumption that you are going to make. The first assumption and the only assumption that you are going to do here is x of t and y of t are said to be having the fundamental period. Say t would be equal to 2 pi divided by omega naught. All right. So now again the circular convoluted, that is z of t, where it is circular convoluted of two signals, two continuous time signals, that is x of t and y of t. So these two signals, once it is convoluted, you are going to get a new signal called as z of t then. Okay, so by definition you are going to have z of k being written as 1 divided by t integral over the time period z of t into e power minus j into k omega naught into t dt. Okay, so this z of t is written as this circular convolution, that is integral over the time period x of t convoluted with y of t then. All right, so that is where you are going to integrate it. So but if you understand the definition of circular convolution, or in general any convolution operation being performed on two signals, okay, so you are going to have L as the new variable which needs to be written over the time period. Okay, so that is x of L multiplied with y of t minus L dl. Okay, so next again by definition you are going to replace it over this integral that is there, that is integral t is equal to the time period and L which is there as x of L into y of t minus L dl. Okay, so that is there as the new thing which needs to be replaced, that is for z of t. So this entire thing was z of t there. So z of t is being replaced with this convolution. So now again e power minus j into k omega naught t dt. So z of k can be written by changing the order of integration. So here changing the order of integration. All right. So now by changing the order of the integration, so z of k is written as 1 divided by t integral L equals over the time period x of L, and again under the bracket you are going to have one more integral. Okay, that is t would be equal to y of t minus L e power minus j into k omega naught t dt. So and you are going to have the integral as dl. Okay, so let me replace it by one more variable there just to make you understand. So I have t minus L that would be equal to m. So let me differentiate it. Okay, so you are going to have dt. Okay, so dt that would be equal to dm there. Okay, so again t would be replaced by m plus n. So by just changing here, I'm going to have y of m e power minus j in k omega naught in the brackets, that is m plus L dm. Okay, so that you are going to replace it as integral L is equal to t x of L e power minus j into k omega naught into L dl, and this one as dm. So t into x of k and t into y of k. So this 1 by t, one of the t gets cancelled, that is the fundamental time period, and you are going to left out with t into x of k into y of k. So we have proved that z of k that would be equal to t into x of k into y of k, that is there. Okay, so it is proved. Right, so this is how I am going to take this, and z of k for any circular convolution, that is z of t being written as x of t circular convoluted with y of t. So you are going to have z of k to be equal to t into x of k into y of k. Okay, so if you want to make a note of it, you can make a note of it. Okay, so just remember z of k would be equal to t into x of k into y of k. Okay, so let me move on to the next one, that is modulation or multiplication theorem. Don't get confused with convolution and modulation or multiplication theorem, what I'm going to do now. So see to it that the identities or the properties of the continuous time Fourier series are clear to you. Okay, so modulation or multiplication theorem. Okay. Yes. So proceeding, I again have x of t. Okay. So you are going to have the Fourier series operation being performed on it, and y of t, you are going to have y of k there. So that is the again the Fourier series. So if x of t, if you take the Fourier series of it, you are going to get x of k, and y of t, if you take the Fourier series of it, it is y of k there. All right. So now multiplication. Okay, z of t, the new signal, that would be x of t into y of t. Okay, so that is x of t into y of t. So what you are going to get by taking the Fourier series, you are going to get z of k, that would be equal to x of k into y of k then. Okay, so z of k, that would be equal to x of k into y of k. All right, so you are going to get it as we proceed with the derivation. Okay, so let me begin with the proof by the fundamental definition of z of k, that would be equal to, okay, so that is 1 divided by t integral, the time would be from total time period. Okay, so now what I'm going to write here, this is z of t into e power minus j into k omega naught t dt, omega naught t dt. Okay, so this is z of t, what you are going to replace. So z of t would be x of t into y of t. So let me replace here, that is 1 divided by t integral, t would be the time period, that is z of t, if you want to give it, that is x of t into y of t. All right, so that is e power minus j into k omega naught t dt. Okay, so that is what you are going to do there, right? So now the synthesis equation, recall your synthesis equation where x of t was defined as sigma, say L is equal to minus infinity to plus infinity, x of k e power j into k omega naught into t. Okay, so now I'm going to replace this equation. Okay, so in x of k, that is, sorry, I'm going to replace here with z of k, sorry, z of k, that is 1 divided by t integral, that is the time period, sigma L equals minus infinity to plus infinity. Okay, so you are going to have the new function, that is x of L here. Okay, so this is the fundamental definition what I write. So here if I want to write it as L here, so if it is L here, this would also be equal to L. Okay, so this would also be equal to L. If it is k here, the summation, that would be k again here. So that is L equals minus infinity to plus infinity, that is x of L, okay, e power j into L omega naught into t multiplied with y of t. Okay, so sigma, yeah, y of t e power minus j into k omega naught into t dt. Okay, so that is there, and again changing the order of summation, what do I get? Yes, can anyone tell me, changing the order of summation, what would you get? How would you change the order of summation? Can anyone tell me now? We have done it in case of convolution in the same similar steps. If you carry out, what would you get? Z of k, that would be equal to 1 divided by t. Yes. Changing the order of summation and also integration. Yeah, what would you get? So sigma L equals minus infinity to plus infinity. Okay, so integral, if I change it, that is x of L is the x of L is there. Okay, so next over the time period, that is y of t e power minus j k minus L. Okay, k minus L into omega naught t dt. So how did I write this k minus L? Can anyone tell me? Yes, are the exponential terms which are there, isn't it? Okay, so once I take the common factor, so that would be written as k minus l, e power minus j k minus l into omega naught into t dt. Okay, so what you're going to get there? What are you going to get? So that would be sigma, okay, L equals minus infinity to plus infinity, okay, x of L into y of k minus L. So this one here, which represents k minus L there, okay, so we are going to take sigma L equals minus infinity to plus infinity, okay, so you are going to have x of L multiplied with y of k minus L. So that is z of k, that would be equal to x of k with y of k there. Okay, the simple multiplication there. So you are going to have z of k, that would be equal to x of k into y of k. Okay, so that is the proof there. I hope it is clear to you. Okay, so you are going to have x of k into y of k there. All right, so you are going to have the order of summation and also the integration being changed. So this entire function over here, okay, so this is where it is being represented as y of k minus l. Okay, so this is there. So that is x of l into y of k minus l. Okay, so one thing that is there. So here we had performed the time domain convolution. You are going to have multiplication. So here the star sign represents the convolution there. Okay, so star sign represents the convolution. Yeah, so here also I think I missed out. So this is the convolution operator, linear convolution to be precise. Okay, so this is the linear convolution. Okay, yes. So if you have any doubts, you can just unmute yourself and you can do let me know. I'll stop sharing now. Okay, if you have any doubts, you can do let me know. All right. So or else we are going to proceed with the final theorem, that is, okay, Parseval's theorem. Okay, shall we proceed? If you have any doubts, you can unmute yourself and you can just let me know, or you can type in the chat box. Okay, so if you have no doubts, shall we proceed to the Parseval's theorem? Okay, I need a confirmation. Okay, shall we proceed to the Parseval's theorem? Okay then.
Yes, sir.
Okay, yes. Let me start sharing my screen now. Okay, so now Parseval's theorem. So after the Parseval's theorem, we are going to have a bit of break and we are going to start a class again. Okay, so at 10:20 we are going to have a break and we are going to have again the other class at 11 to 12. Okay, so see to it that you take break and revise some of the concepts there. Okay, so in Parseval's theorem, so it is with respect to the power spectrum or the power spectrum that is there. Okay, so of any continuous time signal, if you want to find out the power spectrum. Okay, so Parseval's theorem is one such theorem which comes in handy to find out what is the power that is there, that is developed over the one complete time period. Okay, so of any given continuous time signal. Okay, So now I have to identify, say, x of t is the continuous time signal, and it is said to be a power signal there. Okay. So one thing that you need to identify, which is the continuous time signal, that is x of t, which is said to be the power signal. And if you take the Fourier series of it, that is x of k there. Okay. So what is the average power? How we are going to find out the average power of a given x of t power signal? How you are going to find out the average power in a given waveform? Okay, over the time period set t, you are going to have the time period set t. So how you are going to find out the average power p? That is 1 divided by t over the time period that is there. So x of t modulus squared dt. Okay, so that stays again sigma equals k is equal to minus infinity to plus infinity, that is x of k squared. Okay, so if you want to take the average power of the given power signal, the average power is being determined as p equals 1 divided by t according to the Parseval's theorem, and also the general way in which you are going to find out the power. So the average power over one complete time period, that is 1 divided by t integral over the time period x of t, okay, under the modulus squared dt, that would be equal to sigma k equals minus infinity to plus infinity x of k under the modulus square there. Okay, so now let me proceed with the proof here. Okay, so p, let me write down the equation again, that is 1 divided by t, that is there. Okay, so that is x of t squared dt. So that would be equal to sigma k equals minus infinity to plus infinity, that is x of k, the complex Fourier coefficient, and we are going to square the magnitude of it. Okay, yes. So moving on with the proof for it. Okay, so from here onwards, we were like what we are going to do is, like previously we are going to we have assumed that x of t is a real function of t. Okay, so now let us assume that. Okay, so let us assume x of t is a complex value. X of t is a complex value or a complex signal. Okay, so now what would be the magnitude of it? The square root of the magnitude, that is x of t, okay, multiplied with x star of t. Okay, okay. So can anyone tell me what is x star of t?
Sir, conjugate of x of t.
Wonderful, very good answer. So x star of t is said to be the complex conjugate. Exactly. So that is said to be the complex conjugate of the given signal. Okay. So now I have x of t modulus squared, that would be equal to x of t into x star of t. Okay. So now, what would be the case when x of t would be real? So it would have also been the square root of it. So this part which was there, okay, you say that it is real. The imaginary part of the complex wave would be equal to 0 there, right? So now if I take only the real part of it also, the theorem, whatever that was there, that is x of t, that is going to be there. So we are going to take its magnitude, isn't it? So once you don't have the imaginary part, so the real part squared would be the total magnitude of the function there, right? So now let me proceed. That is p would be equal to 1 divided by t integral over the time period, that is x of t squared dt. Okay, so x of t squared dt. So this x of t squared dt, that is 1 divided by t over the time period. What I'm going to take here is x of t and x star of t, that is being multiplied with respect to dt there. Okay, so now this is the substitution what I have done here, that is x of t multiplied with its complex conjugate. So the average power equation would remain the same. Right? So that is the synthesis equation has to be recalled here. Synthesis equation, if I want to recall the synthesis equation, that is x of t, that would be equal to sigma k equals minus infinity to plus infinity, and you are going to have x of k e power j into k omega naught into t there. Okay, so now How do you get the complex conjugate? How do you get the complex conjugate now? So now I have the synthesis equation of x of t. Okay. So how do you take the complex conjugate? It's simple. If you want to take the complex conjugate, it has to be on the both sides of the equation, isn't it? So it has to be on the both sides of the equation. That is by taking the conjugate, by taking the conjugate. Okay, so how we are going to take the conjugate? So if I want to perform an operation on an equation, it has to be there on both the sides of the equation. So you have to remember like that, and you are going to have x star of t, that would be equal to sigma k equals minus infinity to plus infinity, that is x of k, that is also star. So if you take the exponential function which is said to be positive, so it will be negative there. So e power minus j into k omega naught into t. So if you recall the theorem, the same thing what we had done there also, and there we were taking the conjugate also there, right? So that is x star of t, that would be equal to sigma k equals minus infinity to plus infinity x star of k into e power minus j into k omega naught into t. Okay, so now this equation has to be substituted in the integral equation that was there, that was for the average power. So what you are going to get there? So that is p will be equal to 1 divided by t integral, that is there, over the time period, say x of t. Okay, so here it was x star of t, where I'll be representing this equation here. So let me write the equation as sigma k equals minus infinity to plus infinity x star of k e power minus j into k into omega naught into t. Okay, that is there into dt. Okay, so integral x, which was there, this is the x of t, and this one would be for x star of t. Okay, so that was there. Again, changing the order of summation and integration. Okay, you can change it and do let me know the answer soon. Anyone? Changing the summation and integration order. Changing the summation and integration order. Okay, what you are going to get? You are going to get the value of the average power as P, that would be 1 divided by T. Okay, so sigma k equals minus infinity to plus infinity, that is there. You are going to have x star of k, that is there, integral over the time period, say x of t, that is there, e power minus j into k into omega naught into t dt. Okay, so now I have this part of the equation and also the integral part there, right? So if you recall this integral part, that is x of k, and this is 1 divided by t sigma k equals minus infinity to plus infinity x star of k. All right, so that is there. Okay, so now I'm sorry, this one along with the 1 by t equation, which will be there. All right, so I think 1 by t, I have to take it this side. Yeah, fine. So now it is the clear equation which is there. So you are going to have the summation being multiplied with the conjugate complex Fourier coefficient and also the complex Fourier coefficient there, right? So that one, if you take the summation, okay, so if you take the summation, that would be sigma, again from k is equal to minus infinity to plus infinity. So you are going to have the like you are going to have x of k and x of k, right? So what is its magnitude? So you are going to have the squared value of it, right? So this magnitude will come into picture once you are going to take only the the amplitude of it, right? So when I say the amplitude of it, it is nothing but the modulus, that is the magnitude of the given function there, which is x of k. So for example, x of minus 3 would be 2 and x of 3 would also be equal to 2 there, right? So now in such cases, you are going to have 2 into 2, that would be, so that is x of minus k, that would be equal to x of k there, right? So that is 2. Okay, so now if you want to multiply x of k into x of minus k, right? So its magnitude would be the same, 2 into 2. Or what you can write, you're going to have the magnitude of it, you're going to take the magnitude of it and square it. Okay, so this is one simple example which is there, and this is the Parsevals theorem. So if you want to find out the power, so it would be the squared value of it. Okay, so Parsevals theorem, okay, very important one. Parsevals theorem for your competitive exams, you are going to have x of t being the power signal, x of t being the power signal, where p would be equal to 1 divided by t integral over the time period, that is x of t under the modulus squared dt. So that would be equal to sigma k equals minus infinity to plus infinity, that is x of k. Okay, so the squared value of it. Okay, so this is how we are going to take the Parsevals theorem, and the average power of any waveform is being computed like this. Okay, so now what happens if we plot the values? We would like have the linear way in which the power spectrum is being obtained, right? So how we are going to plot the values? You are going to get k value here and x of k under the modulus square there. So if you plot, you are going to get a linear value like this. Okay, so it would be a linear spectrum. So in MATLAB, you would be having the Fourier transforms or the Fourier series block also being there. So it would be similar to this. Okay, so you are going to get the power density spectrum. You're going to get the power density spectrum. Okay, so if you plot against x of k under the modulus squared versus k there, so it would be a linear power spectrum, or they will generally call it as the power density spectrum of the given signal x of t, given power signal, say x of t there. Okay, so this is what the Parsevals theorems say there. So you are going to obtain the average power. You're going to obtain the average power there. Okay, so this is one simple equation that you need to remember. Okay, so it would be better that if you are solving problems related to Parsevals theorem, so where we have to find out the average power and also the complex Fourier coefficients, so this equation comes in very handy there. Okay, so we will stop right now. Okay, we'll stop right now, and meanwhile at 11 we are starting again. Okay, so I want everyone to attend the class at 11. Okay, so let me stop recording.